Hi everyone, today we will talk about divisibility. Since ancient times, people have known that one cannot always separate n objects into k equal piles. This is possible only when n is divisible by k. So, today we study divisibility properties of the integers. Firstly, definition. If a, b are integers with b is non-zero and a is equal to m times b for some integers m, then a is divisible by b, and b divides a. A is divisible by b. So, we call b a divisor. B is a divisor or factor of a. A natural number other than 1 is prime if its only positive factors are itself and y. Let's write a natural number other than 1 is prime. If its only positive factors are itself and 1. The first few prime numbers are 2, 3, 5, 7, 11, and etc. As you see, the factors of 2 is 1 and 2, 1 and 3, 1 and 5, and so on. We will prove that every natural number has a unique factorization into primes. To ensure uniqueness, we must declare that the number 1 is not prime. We will also study integer solutions to linear equations and solve the following problems. So, definition. Integers a and b are relatively prime, when they have no common factor greater than 1, when they have no common factor greater than 1. For example, 3 and 28. As you know, the factors of 3 are 1 and 3, and the factors of 28 are 2, 2, and 7. So, are there any common factors? No. 1, 3, 2, 2, 7. There are no common factors, so these two numbers are relatively prime. But 28 is not prime number. 28 is relatively prime to 3. Lemma. If A and B are relatively prime, if A and B are relatively prime, then there exists integers m and n such that m times a plus n times b is equal to 1. Prove it yourself, please. This is your homework. Here is some propositions. Proposition 1. If A and B are relatively prime, A and B are relatively prime, and A divides Q times B, then A divides Q. Let's see some example. Suppose that A is 3 and B is 5. Let's assume that Q times B is 13. If Q times B is 13, as we mentioned before, B is equal to 5, then Q is equal to 6. And we said that if A and B are relatively prime, then A divides Q. Q can be divided by A. Yes, it's true. Proposition 2. If a prime P divides a product of k integers, then P divides at least one of the factors. What does it mean? Let's see example. 2 times 5 times 7 is 70. Let A be 5. 70, the product of k integers, here k is 3. There are 3 integers, 3 products. The multiplication of these 3 products is 70. If A, for example, 5 divides 70, then it means that at least one of the factors of 70 can be divided by 5. Yes, this is true. 5 can be divided by 5. Another definition. a prime factorization of n expresses n as a product of powers of distinct primes. The exponent on each prime is its multiplicity. What does it mean? For example, let's take 1200. The factors of this is 2, 2, 2, 2, 3, 5, and 5. These numbers, these factors, are the factorization of 1200. These are prime factorization. So we can write it as 1200 is equal to 2 over 1, 2, 3, 4, 3 over 1, 5 over 2. These numbers is multiplicity of each number. Okay, these are prime factorization and these exponents are multiplicity. So now let's write the fundamental theorem of arithmetics. Every positive integer n has a prime factorization, which is unique, except for reorderings of the factors. What does it mean? As we mentioned above, 1200 is equal to 2 over 4 times 3 over 1 and 5 over 2. The result will not change if we reorder the factors. It means that if we write 5 over 2 times 3 over 1 times 2 over 4, if we change the order of the factors, our result will be the same. It never changes. Finally, we can give the definition of greatest common divisor. Given integers a, b, not both 0. The greatest common divisor, the greatest common divisor of A and B is the largest natural number. The largest natural number that divides both A and B. Divides both A and B. By convention, greatest common factor, greatest common divisor of 0 and 0 is equal to 0. Now let's find how to find greatest common divisor by using Euclidean algorithm. Today we will learn also the Euclidean algorithm. What is Euclidean algorithm? So let's find the greatest common divisor of 10 and 45 by using this algorithm. Firstly, greatest common divisor is the largest number which both divide 10 and 45. As you know, the factors of 10 is 2 and 5. The factor of 45 are 3, 5, and also 3. So the greatest common divisor is, as you see, 5. But let's find this greatest common divisor by using Euclidean algorithm. Firstly, we choose the larger number, 45, and we should find how many times the smaller number go into 45. As we know, 10 is 10 multiplied by q plus some remainder r. Here q is how many times 10 goes into 45, and r is a remainder. And here we know that 45 is equal to 10 times 4 plus 5. And as you see, the remainder is 5. We will continue this process until the remainder is 0. So let's continue. Here we got 10. 10 is equal to 5 times 2 plus 0. As you see, the remainder is 0, and here we finish our process. And our greatest common divisor is the last remainder. Here is our another example. Let's find the greatest common factor is of two large numbers. So 3768 is equal to 1701 times some number q plus some remainder. Here q is, as you know, 1701 1 times 2 plus 366. Now, as you see, the remainder is 366. We will continue this process until the remainder is 0. Now, we write 1701 is equal to 3066 times 4 plus 237. As you see, the remainder is still not 0. So we will continue. 366 is equal to 237 times 1 plus 129. Our remainder is not 0 still, and we will continue. 237 is equal to 129 times 1 plus 108. We will continue. 129 is equal to 108 times 1 plus 21. The remainder is not 0 again, and we will continue. 108 is equal to 21 times 5 plus 3, and our final step is 21 is equal to 3 times 7 plus 0. As you see, our remainder is 0. And our last remainder was 3. So the greatest common divisor of these two large numbers is 3. So 3 is greatest common divisor.